Sharpness of resonance. Sharpness of resonance. Sharpness of resonance. Okay. The displacement amplitude of a force oscillator is given by A equal to F naught upon under root of 4b square omega square minus omega square minus omega naught square whole square. Okay. This is the amplitude. This is the amplitude. Amplitude. Okay. And at resonance, the frequency of the applied force is equal to the frequency of the oscillator. Okay. At the resonance, the frequency of the applied force is equal to the frequency of the other oscillator. Okay. At the resonance frequency, the frequency of the applied force is equal to the frequency of the other oscillator. Okay. Then omega equal to omega naught r. Omega square minus omega naught square equal to 0. The amplitude of the force vibration at resonance. Then the amplitude of forced vibration. The amplitude of forced vibration at resonance equal to F naught upon 2b omega where F naught equal to applied force and where F is the applied force per unit mass and omega by 2 pi frequency of the applied force. Frequency of the applied force. Frequency of the applied force, and B is the damping coefficient. Damping coefficient. Okay. And the frequency of the applied force omega increases. At the frequency of applied force omega increases. R decreases from its resonance value omega naught value of the amplitude always decreases. Omega is increased or decreased. Omega is increased or decreased from its resonance value. Omega naught the value of the amplitude always decreases. When the amplitude at resonance falls rapidly as the frequency omega of the applied force is changed. When the amplitude at resonance falls rapidly as the frequency frequency rapidly as the frequency omega of the applied force, as the frequency omega of the applied force is changed slightly from its resonance, slightly from its resonant value. The resonance is said to be sharp. Is said to be sharp. Okay. And when the amplitude at resonance, when the amplitude at resonance falls gradually as the frequency omega of the applied force is changed slightly from its resonant value. The resonance is said to be flat. The resonance is said to be flat. Okay. The sharpness of resonance depends upon damping. The sharpness of resonance depends upon damping. Okay. Sharpness of resonance. Okay. The displacement amplitude of a force oscillator is given by F naught. F A equal to F naught upon under root 4b square omega minus omega square minus omega naught square whole square. Amplitude. Okay. At the resonance frequency of the applied force is equal to the frequency of the oscillator, then omega equal to omega naught or omega square minus omega naught square equal to 0. The amplitude of force vibration at resonance F naught upon 2b omega, where F naught applied force per unit mass omega by 2 by frequency of the applied force, and B is the damping coefficient. Okay. If damping coefficient as the frequency of the applied force omega is increased or decreased from its resonance value, omega naught, the value of amplitude always decreases. Amplitude always decreases. Okay. When the amplitude at resonance falls rapidly as the frequency omega of the applied force is changed slightly from its resonant value, the resonance is said to be sharp. When the amplitude of the resonance falls gradually as the frequency omega of the applied force is changed slightly from its resonance value. The resonance is said to be flat. The sharpness of the resonance depends upon damping. Depends upon damping. Okay. Effect of damping on sharpness of resonance. Effect of damping on sharpness of resonance. Okay. Okay. Effect of effect effect of damping. Effect of damping. Effect of damping on sharpness sharpness of resonance. Okay. Effect of damping on sharpness of resonance. Effect of damping on sharpness of resonance. Okay. You let so when b equal to 0, this is the curve. This is amplitude y-axis, and this is omega. Okay, frequency. Okay, then and this is omega not equal to omega. That means resonance condition. This is the resonance condition. Okay, when b equal to 0. When b equal to 0 is that there is no damping. When b equal to 0, that means damping coefficient is 0, then there is no damping. There is no damping. The amplitude at resonance becomes infinite as shown in the figure. First, at resonance can becomes infinite. Resonance can become infinite. Becomes infinite. You can show this figure. Okay, infinite. Okay, this is the first point. When v equal to 0, there is no damping. The amplitude at resonance becomes infinite. The amplitude becomes infinite. Okay, you can show the figure first. Okay, figure first. Second point. First point. Second point. When damping is small, the amplitude is sufficiently large but falls off rapidly as frequency of the applied force becomes slightly different from the natural frequency of the body. You can show the second figure. When the damping is small, when the damping is small, when the damping is small. Okay, small. When the damping is small, then this curve is this is second curve. This is curve. When the damping is small, the amplitude is sufficiently large. But falls off rapidly. As the frequency of the applied force becomes slightly different from the natural frequency. Okay, this is the curve second curve. Okay, figure second. Okay, third point. As the value of b increases, the amplitude at resonance decreases. You can show by third figure. Okay. This is the third figure. Okay. As the value of b increases, the value of V increases, the amplitude at resonance decreases. The amplitude at resonance decreases. The amplitude at resonance decreases. But the curve and in figure 7 this is 3 and fourth point falls up gradually, and even when the frequency of the applied force is a little different from the natural frequency, amplitude is nearly same. Nearly same. In other words, when the damping is small, resonance is sharp. In other words, when damping is large, damping is small. When damping is small, resonance is sharp. Resonance is sharp. When damping is large. When damping is large, resonance is flat. Resonance is flat. Okay. Amplitude. The amplitude of the force oscillator as the resonance becomes very large. This is because resonance is due to the accumulated effect of a number of successive impulses. Each impulse impart energy to the force oscillator at the proper time in the right direction. The force oscillator and the applied force are in phase. Okay. This happens when there is almost zero damping. If the damping is large, as in the case of an air column, the natural vibration die out quickly, and by the time the effect of say the 10th impulse is coming, that of the first almost disappears. It means there is no chance for the impulse to go out of phase and decrease the amplitude. For maximum amplitude, in such a case, the impressed force should be in phase 13 vibration only, and slight amount of misturning will have no effect. Example. If the damping is small, as in the case of tuning fork, the natural vibration die out very slowly, and when the 10th impulse comes, the effect of the first still persists. The impulses will get out of phase and destroy each other effect, even if there is a small difference in frequency. The tuning therefore should be sharp so that the impressed force and the natural vibration remain practically in phase. Okay. Power supplied by driving force. Next, studying power supplied by driving force. Okay. Elements of boron elements of